Sometimes students will wonder, like, what do you mean you want us to actually know math? I mean, I want you to be able to build from first principles all the way down to scalars every idea that you need. And I want you to be able to prove it for yourself from first principles. This math class is not an exercise in faith. There are places in life where you go and people say, this is the way things are. And then you say, why? And they say, because it is. And that's useful sometimes. Like on Sunday morning, if you go into your temple and the person that's leading it says, you shall believe this, and you say why, and they say because it is, please exercise that faith. That is an exercise in faith. But in math class, this is a very, very sacred space in my mind anyways. In math class, there should always be a logical reason why that you can construct for yourself, and you need not an instructor to tell you that. If I do my job well as an instructor, I should fire myself. Every single one of you at the end of the quarter should say, that guy's useless, because every bit of knowledge that I need in this class, I know from first principles, and I can answer why to every question in this class. When I'm solving a problem, when I'm using an algorithm, when I'm doing a calculation, I don't need somebody else to tell me why I'm doing it. I know why I'm doing it for myself. And not only do I know why I'm doing it, I can map that back to first principles, to the general ideas that I've seen in my life, and I can make connections between that math class and my life outside of that class. That's what I mean. That's what I want for my students. And what it requires from my end is that I push you much harder than showing you a simple example, showing you a solution to that example, giving you a test that looks like the example with different numbers, and then having you mindlessly just plug and chug that example in a different context. No. I want you to be able to construct knowledge. I have a belief down to my core. If I can do it, you can do it better. Every single one of you has the capacity to be a better mathematician than I ever will be. But in order for that to happen, I need to actually empower you to understand this material better than I do at current, or at least earlier in your physical age or mathematical age. That's what I mean in my class. And you'll see this. The entire way that I've structured this class is with that in mind. I am giving you what I never had, but what I yearned for. When I took linear algebra, my teachers basically guaranteed that I had no chance of understanding this subject because they organized it in such a way that it was ass backwards. They taught me the backward problem first, then they taught me the forward problem in the context of another backward problem, then they never made the connections, and then at the end of the day they said, oh yeah, by the way, this is the most important field you'll ever see in your life. Go figure out why. Yeah. Welcome to Anderson's class. I wanted to give you a little context so you're not wondering, like, what is this guy all about? Like, I'm about you all being the best mathematicians that you can be, and me being the wind at your sails, so that by the end of the course you go, I don't need that guy anymore. More on that later. Let's look at this particular problem, and I want to look at a few different scenarios. Let's look at, do you remember the three different scenarios we talked about in the cosine formula? Equal to 90, and then 90 less than 180. If I look at this vector right here as the 2 norm of u, and then I look at this vector right there as the 2 norm of v, what did we say about u dotted with v? What must be true about that? It's going to be less than 1, but greater than 0. Can you show me a rotation and a scale? Well, the scaling factor is not, like, when I take this dot product, what is it giving me? It's not actually giving me a projection. A projection would be a vector. This is the projection vector, and we're going to derive the formula from that from first principles. Is this a projection? Is this a vector? What is it? Yeah, it's a scalar, meaning that it's a length. This dot product is giving me the length of the projection vector. In other words, it's scaling the vector u down, in this case, by some factor, so that the residual vector, the difference between those, is identically what? Orthogonal. That now I have this one and this one, never the two shall meet. There's no part of this vector that is in the direction of that vector, and there's no part of that vector that is in the direction of that vector, and the dot product itself gives me that exact length. It tells me how much of u I need to get directly under the head of v. And the same thing's true in reverse. If I reverse this, then v is on this one and u is on that one, and now I know how much of u is in the direction of v. That's this one, right? Yeah.
Why would it be greater than 0? Couldn't the two be orthogonal and have none in the direction? Oh, yeah.
It's just by assumption, right? This is a classic mathematician's trick. What you just asked me right there was the assumption that what? Yeah, if I have the 2 norm of v and the 2 norm, I guess I should always choose one to be one and one to be the other. If theta is 90, what would you say? What does the dot product measure? It measures, I guess we have to talk about, here's one thing that we might do. Do you remember what we called the thing on the left and the thing on the right? It's the same thing that happens when we get mad at each other. We argue meant each other. We argue, right? So this is the argument on the left and the argument on the right. We might say, which comes first, the horizontal or vertical axis when we're thinking about graphing? Horizontal. So we might say that the left argument, let's always visualize as the horizontal, and the right one, let's visualize as the other one, right? So if I say u dot v, we might think to ourselves, let's figure out how much of v is in the direction of u, or vice versa, right? In this case, how much of v is in the direction of u? What is this dot product if they're both normed 1? 0. Why do you say that it's 0? Because none of v goes in the direction of u. There's nothing there. I can't travel along u in order to get towards v. All right. Could you guess what this one goes for? If I say that theta is like this, well, let's go ahead and say that the argument on the left, we'll call it u. The argument on the right, we'll call it v. U is along the horizontal. V is along the non-horizontal. Now what? What is u dot v? It must be negative. What do we mean it must be negative? What does it mean that u dot v is negative?
They have no...
You got to be careful. Formally speaking, we're going to define direction in lesson 6. Direction means a set of all scalar multiples. It's a span. So formally speaking, when you say not in the same direction, I hear this vector is not a scalar multiple of u. Is that true? Is the red vector not a scalar multiple of u? It is a scalar multiple of u. That's a false statement, right? So is it the case that this vector right there, we might call that the projection vector? Is the projection vector in a different direction than u? No. Another way to say that is the projection vector is in the same direction, but opposite orientation.
And those are different orientation and direction.
Oh, yeah. The direction, if I say, this is the difference between math and English. And this is a non-trivial difference, by the way. The direction of a vector, in this class, we're going to call the span. We're now transitioning into lesson 6, but I'm not formally doing that yet. The span of u, we'll call it, we can think about that as the direction of u. What is it? It's the set of all scalar multiples times vector. In English, what would you say? If I walk like this in English, like my son and I walk sometimes when we're playing, and then I walk like this in English, what would you say about my directions? They're opposite directions. In math, what would you say? Same direction. It's the same direction. Orientation, if I say that u is equal to alpha times, or perhaps I say v, p is equal to alpha times u with alpha greater than 0, can you guess what we say about the vectors u and p?
They have the same orientation.
Same direction, same orientation. Same direction, same orientation. What about this one? What if I say that p is equal to alpha times u, but I say that alpha is less than 0?
Same direction.
Same direction. Why is it the same direction? Is that an English word? No, what type of word is that? Mathematical word. Why do I say that they're the same direction? Because one is a scalar multiple of the other. What does it mean for two vectors to be in the same direction? Vector 2 is a scalar multiple of vector 1. So we got to delete the idea of what a direction is. What does it mean for opposite orientation? The scalar that defines that relationship is negative. And the reason I call this goes back to some of the stuff that we did in 1C. Orientation, I like to think about if this is the tail of the vector and that's the head of the vector, and somehow I've imposed a frame of reference. So I've said that there's a positive direction and a negative direction. Okay, could you guess which way we call positive in this case? Tail. So if I read from left to right, if I read in the positive direction, see what I hit first. What do I hit first? Tail, then I hit the head. So we'll call that positive orientation. Okay, let's take a look at this one. Let's read from left to right. What do I hit first? First I hit the head, then I hit the tail. If we said that this was positively oriented in that direction, first I hit tail, then I hit head. This one, I hit head first, then I hit tail. What do you notice about those orientations? They're exact opposite in that direction. That's why I call that positively oriented and oppositely oriented. Or this one is the opposite orientation of that one, even though they're the same direction. Why are they the same direction again, Irene? What's a direction?
I don't have the formal definition, but like basically, when would we, it's like they're sort of parallel, but like they're...
That's a very, very intuitive geometric argument, and my claim is you do have the formal definition.
Sorry.
Can we have you move back a little bit? I forget your name right now because I only read it like 4 times. Nand. Yeah, of course I should know that. Nand is my favorite gate. It's a great gate. The Nand gate is a beautiful gate. It's almost as good as the XOR gate, but not as good. No offense. I can't wait till I meet an XOR. That would be awesome, right? What's the formal idea of a direction? It's the set of all scalar multiples times a vector where which scalar multiples am I allowed to choose? Any. I'm allowed to run through every possible scalar multiple I'd ever care about. What's a direction?
So, oh, I see. Okay, so it's a set of all possible scalar multiples
Of that particular vector.
Okay.
Yep, you got it. And then you can think they're in the same direction when they're basically quote unquote parallel. One of them can be written as a scalar multiple as the other one.